Hi, I'm Zor. Welcome to Zor Education. I would like to start the new topic, the vectors. Well, I'm pretty sure that everybody actually heard the term vector. Okay, what's the vector? That's what it is, right? Well, yes and no. As usual, everything is much more complex than it seems to be from the beginning. So I would like to start from some philosophical concepts. We know that mathematics is basically an abstraction. It's all about abstractions. For instance, the concept of a number is an abstraction from quantity, basically. So people do understand what quantity is, and to represent the quantity, they invent numbers. And also numbers can be used to represent lengths, distance, and some other things. Now, there are other aspects of our life or science which are very important, and they need this abstraction to research, to deal with this mathematically. And this very important concept, which I would like to right now to present to you, is the concept of direction. So this arrow actually represents some kind of a direction, right? So the concept of direction is very important, and not only from the abstract standpoint in mathematics, it actually plays extremely important role in science, in physics, in chemistry, in even in control of some process like oil refinery, whatever. I mean, it's really very, very important. So mathematicians needed to abstract out this particular concept, and they did it, and the vector is actually an abstraction which includes in itself the concept of direction. But it also includes the concept of quantity. So if number is an abstraction from quantity, vector is actually an abstraction from both quantity and direction. So if you take an object which has these two properties, the quantity and direction, then you can actually represent this object mathematically as a vector. Now, the elementary example is a point which is moving somewhere, and the speed, the absolute value, how fast it's moving, is represented by a number, let's say miles per hour or kilometers per second, but the direction is represented somehow. And that somehow is actually what I'm going to talk about right now. So, if you combine the distance and direction of movement, you can have something which can be called a displacement, right? So, if you combine the speed of movement, the absolute value of speed and direction, you can have another interesting term, which is velocity. So velocity is basically a vector which combines in itself the quantitative side of the movement, how fast you move, how many meters per second or whatever, and the directional side of the movement, so where you are moving. Okay, there is one important concept related to direction which I would like to address right now. What's important is not only just direction as a term by itself, it's important where exactly you are moving. So you can move, for instance, along the line, or you can move on the plane, which is represented by this whiteboard, or you can move in space, like a rocket which moves to the moon. Or movement can actually be much more complex than that, and in different spaces. So basically the concept of a space is something which I would like to bring to your attention. Space is where the movement takes place. or if you wish, where exactly this directional characteristic of a vector is located. Now, space is very important, and I have already just gave you 3 examples of the space. One space is the line, and the vector on the line should represent, again, 2 things, like quantitative and directional characteristics. Now, for instance, we are talking about a point which is moving along this line. Now, obviously, it has certain speed characteristics, like how many centimeters per second it covers. It might be constant if it moves constantly with the same speed in the same direction, or it can be variable, but at any given moment we can talk about speed, which is how fast it's moving. But at the same time, we can talk about the direction, where it's moving, to the right or to the left. Or if we introduce the coordinate system, thus the point moves towards increasing the coordinates or decreasing the coordinates. So, how can we represent this particular vector, which combines the quantitative part, which is how fast it's moving, and directional part, where it's moving? Where actually it's very easy. On the line, since the speed of the movement is basically the real number, and it's positive. I mean, if we're talking about just how fast it's moving, it's just a positive number. How many centimeters per second is covered. But if we will add the sign to this, associating the positive sign, the positive speed, with movement towards the increasing the coordinates, and negative numbers with decreasing the coordinates, then speed by itself, let's say 5 centimeters per second, with some kind of a sign, plus or minus, this together characterizes the vector of movement, because it has an absolute value, how fast it's moving, and the direction. In this particular case, it moves covering 5 centimeters per second towards the increasing the coordinates. So that's the representation of the vector on this particular line. Now, can it be represented in more graphical form? And I will definitely talk about this in other lecture. Yes, absolutely. It's basically very easy. You can have three, four, 5. What you can do is you can draw an arrow here which ends up at the point 5 and say, okay, this particular arrow represents my vector. It has nothing to do with the position of the point. Position of the point can be anywhere on the line, but the velocity, the speed and direction of its movement can always be represented as the arrow which starts at 0 and ends where exactly the numerical characteristic ends up, with a proper sign, +5 or -3 or whatever else. So we're talking about numerical and the graphical representation. But I was talking about space, right? So in this particular case, we're talking about a one-dimensional space. Now, why is it one-dimensional? Because if we introduce the coordinate system, it's enough to have one number, one real number, to represent a position. And if something is moving in this particular space, then velocity of this movement can be represented also on the same line using either the arrow or some kind of a number. So position and the vector itself are represented in a very similar way by one real number. Position can be anywhere, and the velocity can be basically any real number. All right? Now, let's talk about some other spaces. Well, the next, from the complexity standpoint, is the two-dimensional space. So let's consider we have a point which is moving somewhere on this whiteboard. Again, what we can do is we can always draw some kind of an arrow saying, okay, well, that arrow represents the velocity of this particular line. The length of the arrow represents the value of the speed itself, the magnitude of the speed, the absolute value. And the direction represents, well, the direction, where exactly it moves. Now, in coordinate system, if we introduce some coordinate system, the position of the point is always two numbers, right? Abscissa and ordinate. Now, if our point moves towards this direction, then I can always use this particular arrow, putting it in the beginning of the coordinate, originated from the origin of the coordinate, and say that this arrow represents the speed, basically, right? Because it represents direction. It's the same direction, right? And it represents the quantitative characteristic, the magnitude of the speed. Now, going into a little bit more complex case, let's say you control some oil refinery or something like this. There are many parameters which are changing all the time. If you just look at probably have some kind of a dashboard or whatever, where all these parameters are somehow brought together through some gadgets and widgets, etc. Now, a state of this oil refinery is a set of all these parameters taking a particular value at a particular time. And then this state is changing. So you are talking about hundreds of different parameters changing at the same time. Now here we have only two parameters, abscissa and ordinate. But in case of an oil refinery, you have hundreds of parameters. Now, they do actually represent the movement, but in this case, it's not two-dimensional space. It's the dimension which is basically equal to the number of parameters. Let's say you have 100 parameters, so it's a 100-dimensional space, and the vectors do exist in this space as well, because since our oil refinery is changing, all the parameters are moving somewhere, so the point which represents a position, a state, if you wish, of our oil refinery at any given moment, this point has 100 coordinates, and it's changing these coordinates, so the point is moving in the 100-dimensional coordinate space. And we have to represent the vectors over there as well, because we have to control this particular oil refinery. So all the parameters should be within certain limits. They shouldn't change very fast. The temperature cannot rise very fast or fall very fast or something like this. And same thing with, I don't know, something else. And if some parameter, let's say, falls faster than it should, well, this is something which we have to really pay attention to. So that's why it's very important to understand that together with the concept of vector, which includes in itself the magnitude and the direction of movement, we really have to understand the concept of a space where this movement takes place. And as a final example, before I complete this introductory lecture about vectors, it's about special theory of relativity, Einstein's creation, where the space where things take place is four-dimensional. It's 3 dimensions of our coordinate system, Euclidean coordinate system, plus time. So now you have 4 parameters which characterize the position of something in this world. Time and 3 spatial parameters. and there is a special geometry there, and there are vectors over there. I mean, these parameters are changing. Time is changing as well as the spatial coordinates. So this is a perfect example of a four-dimensional space where vectors exist and they must be researched somehow, etc. Vectors are very convenient in physics. Many processes, not only the mechanical movement is represented as vectors in physics. For instance, the force. Force is basically a vector because it has a magnitude and direction where it moves. Like the force of gravity, for instance, in this particular point depends basically on two things: the mass of the Earth, the mass of the subject, which is basically gravitated towards the Earth, and the direction. Direction is vertical down. So the vector, which represents the force of the gravitation of the Earth, is basically something like this arrow, or you can represent it in many other ways, but for instance it's an arrow. The length of the arrow is the magnitude of the force, and direction is down. Now, if you are talking about some kind of a spot in a solar system where you have the gravity of the sun and planets and some other formation in space, then it's not so obvious where the vector is basically directed, and it's probably changing as the time goes by. You circle around the sun and your vector is changing. And even in this elementary example of my gravitation towards the Earth, well, in a big picture, considering the space we are in, as the Earth is rotating, obviously this vector is also rotating together with the rotation of the Earth. So basically what I would like to say, that vector algebra, as it's sometimes called, is a very important part of the mathematics and very useful for many practical purposes or science purposes, research, etc. So that's it for today. I am planning to have more information, more general introductory style information about vectors and their representation. And then we will probably devote a lot of time, basically, operations on vectors, and as much as we dealt with operations and numbers like multiplication, addition, etc. I mean, we will have some similar things in the vector algebra as well. Well, that's it for today. Good luck. Hi, I'm Zor. Welcome to Unizor Education. I would like to continue this overview of vectors. It's not really the real research or real theory. It's just basically illustration of what vectors are and how to deal with them. And let me just recall that we were using graphs to basically understand better how functions behave. Similarly, the geometrical representation of vectors is used more for illustration purposes rather than for analytic calculations or whatever else. So today I will concentrate primarily on geometrical representation of vectors. So we know that vectors are objects which have two major characteristics: the magnitude and the direction. It's very important to understand that if we are talking about direction, we have to really think about certain space where this direction is pointing to. If we are talking about vectors as representing, for instance, velocity of the moving point, then this moving as action occurs in a certain space. If we are talking about vectors as the representation of the force, for instance, gravitational force, again, it's applied to certain objects which are located in space. So direction as a concept is always related to the concept of a space. Okay, so what kind of spaces where things are moving or forces are acting can we talk about, and how can we interpret geometrically or graphically, if you wish, the vectors in these spaces? Well, let's just consider a few examples. Let's first think about a point which is moving along the straight line. Okay, so this is the straight line. The point is moving, so this is the point, and we would like to express in the vector form, in the graphical form, the vector of its velocity. Okay, velocity has an absolute value, a speed, how fast the point moving, and the direction. Well, there are only two directions, right? So basically, the typical representation which is used in this particular case can be just an arrow which has the lengths. This is the length of the arrow, equal in some units of measurements to the magnitude of this movement, of the velocity of this movement, and the direction, this arrow at the very end, represents the direction along the line where actually the movement occurs. Now, what if a point moves not along a straight line, but along some kind of a curve? Can we represent the velocity as a vector in this particular case? Well, yes, because if the point is positioned, let's say here, and moves this way along the curve, what usually is used is a tangential line, tangential in this particular point, and again, it's an arrow which has the lengths equal to the absolute speed the point is moving, and the direction is towards this side of the curve where the movement actually occurs. Okay, now these two cases represent a so-called one-dimensional spaces. So straight lines and curves, they are one-dimensional. Now, why are they called one-dimensional? Well, primarily because we can introduce the system of coordinates, which means we have to introduce the beginning of the coordinates. Let's say this is point 0, and the unit of measurement. And if we will introduce these two things, then every point on this particular straight line can be characterized by one and only one real number, which basically is the distance from the point 0 in these units, positive on this side and negative on that side. Now, with the curve, situation is exactly equivalent. We can always find some kind of a point 0, and again, using this particular unit of measurement, we can measure 1, 2, 3, 4, -1, -2, etc. So, point on a curve will also be defined by some real number. Of course, I'm not touching more complicated issues about what is the length of the curve, which is not defined. I perfectly understand that this is something like higher levels of mathematics. But intuitively, you obviously understand that if the curve is smooth enough, then the lengths can be defined, as well as tangential line. I was talking about tangent to a curve, and again, not every curve has a tangent in every point, but we're talking about smooth cases when tangents do exist, and in these cases, we can talk about representation of the velocity as a vector. Now, how about two-dimensional cases? Well, two-dimensional case, first of all, is obviously a plane. let's say the surface of this whiteboard is a plane, and again I can introduce the system of coordinates here, and obviously position at every point is defined by two coordinates, abscissa and ogee. Okay, fine. Now, what if the point is moving? Well, when it's moving, again, it's moving on the surface, on this plane, and at any point we can always have some kind of a arrow which represents a vector of the velocity of this movement. Or if there is some kind of a gravitational force which is directed down, that also can be represented as an arrow in this particular direction, down. And the magnitude of the gravitational force is reflected in the length of this arrow. So that's how we can graphically represent the vectors in a two-dimensional space. A little bit more interesting example of the two-dimensional space is, let's say, a sphere, for instance, or the surface of our planet, which, you know, roughly can be considered as a sphere. Now, it's not a flat plane, obviously. However, it's also a two-dimensional surface. Like in case, for instance, of our planet, you know that we have longitude and latitude. These two coordinates define the position of every point on Earth. So again, since two numbers, since two numbers needed to signify, to determine the position of the point, the surface is called two-dimensional. Now, what's interesting is that, well, it's not as obvious in case of a plane, but in case of a, let's say, spherical surface, and there is a point moving, let's say this is an equator, and the point is moving along the equator. Also, the vector would be tangential to the trajectory of the movement. So wherever the point is moving, whether it's on a sphere or on a plane or any other two-dimensional surface, the trajectory will, on this particular surface, will be some kind of a curve, and the vector which represents the velocity of the point moving along this trajectory will be a vector, will be an arrow which is tangential to the curve. All right. Three-dimensional space. Well, obviously we have vectors in three-dimensional space as well. Three-dimensional space is the one which we live in, or at least we thought. We used to think that we live in a three-dimensional space until Einstein disillusioned us with theory of relativity, adding the time as another coordinate. So this is x, this is y, this is z, abscissa, ordinate, and how's it called? Applicate, right, the third coordinate. So the position of every point is defined by three coordinates, x, y, and z. Now, again, if this is a point which is moving along certain trajectory in space, we can always think about a vector represented as an arrow which points towards its tangential to the curve in a three-dimensional space. Now, what's the example of a curve in three-dimensional space? Let's say a spiral, right? Helix or something. So it's tangential to the trajectory, but it's a three-dimensional vector, which means this particular arrow has a direction and the length, but it's all in 3D, in space, like from here to there. What's also interesting is that how this particular thing is changing with the time. Well, if the point is moving uniformly along this particular curve, uniformly in terms of constant speed, the length of this vector is not changing, only direction is changing, right? Now, if this is a straight line somewhere in space or on a plane or wherever, and it's a uniform movement, then vector actually is exactly the same. It's the beginning of the arrow is moving along the straight line, but the length of the arrow is the same and direction of the arrow is the same. So all these vectors are actually the same. And here is something which I would like to point out. We are talking about vector as something which has a magnitude and a direction, which means if two vectors have the same magnitude and the same direction, then they are actually equal, right? So if we will have, let's say on the plane, and let's say we have coordinates even. If we have this vector represented as an arrow which has certain magnitude and certain direction, and this arrow which has exactly the same direction, it's parallel, and the magnitude is the same, well, then these two vectors, we are saying they are equal to each other, or congruent, whatever the term you prefer. So that's why we can always consider only the vectors as errors originated in the beginning of the coordinates. So if point is moving along some kind of a curve, so this is another vector, what I can say is that this vector, which is the same as this, and this vector, which is, let's say, the same as this, are two different vectors which reflect the velocity of this particular point at two different times. So the velocity is changing from this to this. And it's exactly the same as I'm saying that the velocity is changing from this to this, because these two vectors are considered to be completely equal or congruent to each other. So that's why the manipulation with vectors is always more convenient if you bring all the vectors to the beginning of the coordinates. Later on, we will talk about like addition or subtraction of a vector, or multiplication of the vector or something. And in these cases, it's very convenient to forget about the origination point of this particular arrow. It's more convenient to originate them all from point 0, because these are exactly the same vectors, and that's why the result of the operation would be exactly the same. What else I wanted to talk about? Geometrical representation. Well, basically that covers more or less. The most likely examples which we will be dealing with will be about vectors in a two-dimensional space, which I will use the whiteboard actually as the graphical representation. But again, don't forget that this is just a graphical representation, these arrows. It's just to illustrate better how to deal with vectors, how to add them, how to subtract them, etc. The analytical representation of vectors using the system of coordinates, which will be covered in the next lecture, is kind of more useful, more precise, and that's the real science, or the real math, if you wish. This, again, is no more than illustration, in as much as graphs are illustrations to behavior of the function. It's very convenient to see it this way. Now, also should be mentioned that vectors is something which really is very much used in physics, in different areas of science, etc. Well, that's basically it. These are still introductory lectures about vectors. The real theory will be further on when I will finish with all the overview kind of things. Next lecture will be about analytical representation of the vectors, and only then I will start thinking about a little bit more theoretical lectures with problems, examples, etc. Well, thanks very much for today's lecture, and good luck. Hi, I'm Zor. Welcome to Unizor Education. We're talking about vectors and their representation. It's still part of the overview about vectors. So, after introduction of the concept of vectors and certain time devoted to geometrical interpretation of the vectors as basically directed segments in some space on a straight line or on a plane or in a three-dimensional space or anything. So after that, well, I have to say that, well, the picture is worth 1,000 words, of course, but mathematicians do require certain precisions, and pictures are used for illustrative purposes. It's like graphs for functions. We can use the graphs to basically understand how the function behaves, but concrete analysis of the function is probably impossible without formulas like y is equal to square root of x. I mean, it's nice to have a graph of it, but we do need a formula and the way to calculate certain things to deal effectively with this. So, same thing with vectors. They need some numerical representation. And here's how it's approached. Well, let's consider for simplicity the movement of the point along the straight line. So here is the straight line, and obviously whenever we are talking about some numerical representation of physical movement, we do need coordinates, right? So we do have 0 point, and then 1, 2, -1, -2, etc. Now, here is the point somewhere, and it has certain velocity moving on this particular straight line. And let's say the direction of movements is towards increasing of the coordinates. And there is a certain numerical characteristic of this speed, which is a positive real number, whatever the number is. Now, we can always represent this particular velocity with a signed real number, where the absolute value is equal to the speed itself, and the sign corresponds to a direction. If direction is towards increasing of the coordinates, then the sign would be positive, and otherwise it would be negative. So one real number would represent a velocity, not just the speed. Speed is represented by absolute value of this number, but the velocity is represented by both absolute value and a sign, which is an entire real number. So velocity of, let's say, +5 means that in every unit of time, this particular object is moving 5 units of space towards the increasing of the coordinates. And the velocity -5 means that with the same speed of 5 units per unit of time, 5 units of length per unit of time, it moves towards decreasing of the coordinates. So one real number. And what's interesting is we are talking about the straight line, where the position is also determined by one real number, whether it's on this side of the zero, on that side, positive or negative. So there is some kind of a correspondence between how we determine the position of the point and how we determine the speed of the point. Both can be represented as real numbers. Of course, they have nothing to do with each other. Position can be +25 and the speed can be -5, which means from the position 25 it moves to the left on this picture with a speed of 5 units of time lengths per unit of time, which means after 1 unit of time it will be 20, another unit of time it will be 15, then 10, etc. 5 per each unit of time. But in any case, what's important is the correspondence of the dimensionality. One-dimensional line, and we need one real number to represent position on this line and the speed on this particular line. That's very important. Now let's go to the two-dimensional case. Well, in two-dimensional case, we have two coordinates, abscissa and ordinate, and every point is defined by its two coordinates. Now, let's consider this is a ball rolling freely on the plane along a straight line with a constant speed, and geometrically you can always express it like this, where this arrow represents a direction and the length of this segment represents the speed. Obviously, the faster it moves, the longer would be this particular geometrical representation of the vector of speed, of velocity. All right. Now, can it be numerically represented? Absolutely. What we need is to determine direction and the magnitude of this vector, right? Because that's what defines the vector. Direction is this one, but that's the same thing as this one. If these lines are parallel, the direction is the same, this direction, right? And the lengths I will use exactly the same. Now I will use coordinates of this point and say, okay, the vector of velocity of this particular ball at this particular point is a comma b. So two real numbers which determine the end point of the vector, which is exactly the same by its magnitude and pointing to the same direction as the velocity of this particular ball, this endpoint, the coordinates of this endpoint define the vector. So vector is defined by two real numbers. By the way, again, correspondence, two-dimensional plane, two real numbers to define the position, and two real numbers to define the velocity. So what I'm saying basically is, now, okay, let's go to a three-dimensional case just to make the whole thing complete. In the three-dimensional case, let's say it's a rocket, which is just flying towards the, I don't know, Mars by inertia, just no engines working, etc. So it's straight line in the three-dimensional space. It's exactly the same thing. I can go to the beginning of the coordinates, wherever the coordinates are. Maybe they're centered at some sun or some star, whatever the coordinates are. Go to the beginning of the coordinates in this three-dimensional coordinate space, and I will draw a vector which has the same direction as our rocket is flying, and the length of the vector in some units of measurements corresponds to the speed of this particular rocket. And I will say that this particular vector represents the movement, the velocity, and its endpoint, which in this case will have three coordinates, abscissa, ordinate, and applicate, would determine the vector. Three-dimensional case, three coordinates for position, and three numbers, three real numbers, which represent the vector of velocity in this case. The point I want to make is that there is this correspondence between the dimensionality of the space vectors are operate and the number of real numbers which are sufficient to determine the magnitude and direction of the vector, which basically define the vector. And now let's go to a completely different case. Let's say you're operating in let's say, oil refinery. Now, this is a very complex facility, and it has, let's say, 100 parameters which basically determine how everything works. Parameters of every particular component of this oil refinery. Let's consider that there is 100 of them. Now, every one of these parameters obviously is changing as the time is changing, obviously within certain normal limits. Now, if we would like to somehow determine this change in the parameters, well, in the language of mathematics, it's a 100-dimensional space, so to speak, because it takes 100 parameters to describe the state of the whole system. And every parameter is some real number, so we need 100 real numbers to define the state of the system. But how about vector? Well, actually, it's very, very similar to this one. Because what we can do is, we can check how much each parameter is changed during the unit of time. And that's also some kind of a real number. Now, the set of all these real numbers, and there are 100 of them, of course, because there are 100 parameters, so there are 100 changes. These real numbers would characterize the magnitude and the direction where exactly the parameters are moving at any given time. So it's completely different, not geometrical and not even represented as a vector, geometrical vector kind of a situation. But still, you can use an ordered set of numbers. Now, ordered because obviously the parameters are meaningful. I mean, the first one is the pressure, the second one is the temperature, etc., etc. So it's ordered set of numbers which define the vector. And in this case, it's a vector of change of parameters. In all the cases I was talking about, this ordered set of numbers, the real numbers, actually describes or defines or represents, whatever you wish, a vector. And the number of these parameters, number of these real numbers which define the vector, correspond exactly to the dimensionality of the space this vector operates. So, right now we can forget about graphical representation of the vectors as segments with an arrow somewhere in real space, 1 or 2 or 3 dimensional. We can't define the vector in this case for a 100-dimensional oil refinery, right? But we can instead say that any set, any ordered set of real numbers represents a vector in n-dimensional space. Now, if you want to keep the geometric representation of this, you can view this as coordinates in n-dimensional space of the end point of the vector, where the beginning of the vector is at the origin of the coordinates. So let's say we have a 3-dimensional space, and you can have this point. The coordinates are A1, A2, and A3. So this would be A3. And this particular point is actually representing this vector. So, let's forget about geometric representation, and let's think about the ordered, sometimes people are using angle brackets, sometimes the round brackets. In any case, let's use this particular representation of vectors. Now, it's more generic. That's number one. Number two, it's precise because these are numbers and we know what to do with numbers. We can add them, we can multiply them, etc. We cannot say exactly the same with segments. I mean, sometimes we can, sometimes we cannot. I mean, there are certain restrictions on the geometric representation, but with numbers we can do anything we want to. Multiply, divide, add, etc., etc. And that's what would define the characteristics and operations of the vectors much more precisely. Well, this ordered set of numbers is called tuple in mathematics. So in this case, you might call it n-tuple, which means the tuple which contains n components. Obviously, the vectors on the straight line can be defined as one tuple. The vectors in the plane as two tuple. The vectors in the space as three tuple, and the vectors in the Einsteinian theory of relativity, where the time also is a coordinate, is a four tuple. So that's basically it for this particular representation. Now, why it's important? Because, as I was saying before, this numerical representation allows us to operate on any dimensional vectors, including the vectors which describe changes in the oil refinery, with numbers, which is much easier. It can be computerized, obviously. So that's the most important purpose. That's basically it. So there are two representations we were talking about. The graphic representation, which is more for illustration purposes, and I will definitely use graphical representation, the pictures, the geometry of the vectors, to illustrate certain properties of the vectors. But at the same time, we should not forget that the precise implementation of vectors are through tuples, through ordered set of numbers, and that's what probably would be used to define operations on the vectors, etc. So I will define it using this, but I will illustrate it using geometric representation. All right, so that's it. Now you know another representation, the tuple representation of the vectors, well, there are much more information about vectors which I'm planning to share with you. Thanks very much, and don't forget that Unizor contains all these lectures, so you can re-examine them again. These lectures are not really supplemented with any problems. These are introductory overview kind of things. Problems will be later. Thanks a lot and good luck.